Hi, everyone. Thanks so much for joining us today. Hope you're all doing well. I'm John Diamond. I'm the president of the Humane Alumni Association. We're an independent organization of 110,000 Black Bear alumni. Our members live in all 50 states, the District of Columbia, and more than 100 countries. So we welcome all of you, including the folks from outside the United States who are maybe watching today. Today's webinar offers us a thought-provoking concept. What if the moon didn't exist? What would it mean for life on Earth? Our presenter is a distinguished scholar and a longtime faculty member at the University of Maine. That's Dr. Neil Comins of the Physics Department. He's an astrophysicist, a popular teacher, a prominent researcher, and a prolific author, more than 20 published books alone. He's the real deal. Professor Comins will be taking questions following his presentation today. And if you'd like to ask questions, you can submit that at any time, and we will present those to them. And here's how you can ask your questions. Go to the bottom of your Zoom screen, and in the middle, you'll see the chat button. It looks like the speech bubble you see in comic strips. To submit a question, just click on that bubble, type in your question, and hit the enter or return key on your keyboard. We'll get to questions later in the program, and we'll cover as many of them as possible during the time we have available. And just so you know, we are recording this session, and we will be making it available online later. So for those of you who are watching the recording of this, welcome. I know we have many schools that will be taking advantage of this great opportunity to hear from Dr. Comins and to hear about this fascinating topic. So let's get started. Dr. Comins, the screen is all yours.
Excellent. Thank you very much, John, for the very kind introduction. Hello, everybody. I'm really grateful for you to have tuned in, and I hope that you enjoy what you're about to learn, because it is, in the words of Monty Python, something completely different. So let us begin. Now, if all went well, you can see the title page. I'm sure they'll let me know if otherwise. And what I'm going to do is explore the history of the moon as it really occurred. And by doing that, I hope to give you enough information so that at the end of the talk, we can say, okay, let's take all of these things away and see what would be left, what the Earth would be like if the moon had never formed. Okay, so as far as we know, the current theory is that the moon formed from a collision between the early Earth and a Mars-sized body. And that collision obviously had a tremendous effect on the young planet. And also, I should say that like throwing a rock in a pond, it literally splashed a tremendous amount of debris off of the young Earth and the impacting body. And that debris went into orbit around the Earth. And it initially formed a ring. So the Earth had a ring. When the moon first formed, the Earth had a ring around it, as you can see in the middle of this diagram. If the debris had been too close to the Earth, that ring would still be here. The gravity of the Earth would have prevented the moon from forming. But fortunately, as it happens, the moon's debris formed far enough away that over millions of years, the debris coalesced to form the moon. So we had a moon forming after the Earth originally formed. Now, there's a common belief that the moon orbits the Earth. You've probably heard that before. The moon orbits the Earth. And that is not true. The reality is that the two bodies, the Earth and Moon, orbit a common, we call it center of mass. But let me show you what I mean here. Consider this wrench here. The red X is the center of mass. It's the place where if you put your finger on, put it on your finger on the red X, the wrench would stay there. It would be balanced. It wouldn't fall off your finger. That's called the center of mass. Okay, so if you were to take this wrench, put it on a smooth table, spin it and give it a push, the center of mass would move in a straight line and the sides of it would spin around that center of mass. And what does this have to do with the Earth and Moon, you may well ask? Well, the Earth and Moon are doing the same thing. The Earth and Moon are orbiting around the common center of mass, which we call the barycenter. I've labeled it here, the barycenter. It is this point that follows the curve that we teach as the orbit of the Earth. So the Earth itself is not following this elliptical path. The Earth is vibrating or oscillating around this point. So when the Moon is over here, most of the Earth is up here. The barycenter, by the way, is 1,067 miles under the Earth's surface in a straight line between the centers of these two things. And then the Moon, when the Moon is here, the Earth is there, and so on and so forth. And when the Moon is on the opposite side, most of the Earth is on the opposite side from where it was originally. And the so what about this is that as the Earth is orbiting around the barycenter, the water on the Earth is spinning with it. And because of this motion, some of the water on the Earth is being pushed away from the Moon as the Moon orbits. And so let me pull up another picture here. So as the Earth is orbiting around the barycenter, the water in it is being pushed away, is being spun away. That's a good way to put it, is being spun away from the Moon. And therefore, on the side of the Earth, away from the Moon, on this left-hand picture, on the right side here, the water on the side away from the Moon is being pushed away by this motion of the Earth around the barycenter. And therefore, that creates a high tide. So the high tide on Earth, with the water being pushed away from the Moon side, that the high tide on the far side of the Earth from the Moon is created not by the gravity of the Moon by itself, but rather the motion of the Earth spinning or orbiting, if you like, around the barycenter. At the same time, on the side of the Earth closest to the Moon, the gravity of the Moon pulls the water on this half of the Earth towards it and creates a high tide over here. So there is a high tide on the Moon side, there's a high tide on the opposite side, as you can see on the drawing on the right, but they are made from different sources. The far side one from the motion of the Earth, the closer one from the gravitational attraction of the Moon. And if you're interested in this, if you Google the NOAA website under Our Restless Tides, they'll walk you through the details of how all of that works. So we have now the Moon and Earth orbiting together, dancing, if you will, around the common center of mass. I mean, you can think of this also as, you know, if two people are literally waltzing down the floor, as they spin around and go in a path, both of them are moving around that center of mass between them. It's the same concept as we're talking about here. Okay, so what I described before was just due to the moon Earth system orbiting around the barycenter. But the Earth is also spinning. So I want to put that spinning part back into this story. And that's done in this drawing. So here's the moon. We'll stay with this moon over here. It doesn't matter. These are just two phases of the moon with the sun on the left. But anyways, consider the high tide closest to the moon. As the Earth is spinning, it's going counterclockwise and the moon is orbiting counterclockwise. As the Earth is spinning, the Earth, pulls the high tide created by the moon. It pulls it ahead of the moon in its orbit. So in other words, the high tide, see if I can go back. Yes, the high tide that is directly under the moon here, okay, is actually 10 degrees ahead, the high tide, the water here is 10 degrees ahead of the moon in the moon's orbit around the barycenter. And the so what about that is, if you consider these arrows represent the horizontal red arrow is the force of gravity from the moon, Earth, oops, sorry, let me go back. The red arrow on the side is the force of gravity from the Earth on the moon, pulling the moon towards the barycenter. The yellow arrow is the force of gravity from this water closest. There's a high tide on the other side, but it's farther away. So the force of gravity from this side is weaker than the force of gravity from this side. This water, this high tide, which is leaving the moon in its orbit by 10 degrees, okay, is literally pulling on the moon forward in the direction of its orbit, which is this little red arrow here. Now, conceptually, it's easiest to visualize this as follows. Imagine you had a ball on a string. The ball is hanging down, you're holding the string in your hand, and you start spinning around. You know exactly what's going to happen. The ball is going to spiral outward as it spins around because of the motion, the force given to it by the string connected to your hand. So the ball will spiral outward. Likewise, the moon will spiral outward due to the high tide closest to it, pulling it in the direction of its motion, of the moon's motion. Am I saying that the moon is moving away from the Earth because it is getting energy from the gravity of this water, like the ball on the string? That's exactly what I'm saying. That's exactly what I'm saying. So this has been established for many, over 100 years, but to prove that this is happening, the astronauts, and this is the Apollo 11, the first flight on the moon, put on the moon a device to measure to help us measure whether the moon is moving away as predicted. So just briefly, you can see the lander here. This is a camera, which is a 3D camera, it has two lenses. They put it on the soil, pull the trigger on the top here, and it takes a picture, two pictures, and it's like the Viewmaster stereo pictures that you've probably seen. And therefore, using this camera, they made 3D pictures of the surface of the moon, which are available back here on Earth. This device here measures the vibrations of the moon. Does it have moonquakes? And the answer is yes. And here's Buzz. Oh, it was interesting. I was at a New Year's party once, and I was talking to this guy. He got a Buzz, no pun intended, on his cell phone, and he opened it up and it said, "Happy New Year, Buzz Aldrin." This is the instrument I want to bring to your attention. It's called corner reflectors. And what they are is the same concept as the red and orange plastic reflectors that are on your car, so that when light from another car is aiming at your car, even if your headlights are off, the light from the other car will hit the corner reflector and it will bounce and come straight back to the driver of the car coming towards you to tell you that there is a car ahead of them. And so they put these analogous corner reflectors on the moon so that we could send laser beams from the Earth to the moon, bounce off the corner reflectors, and come back to the Earth. And the big deal about that is we can time the round trip. Send a pulse of light, see how long it takes to get there and back, about 2 seconds, and do the same thing tomorrow and the next day. And every day that they did this, the round trip was longer and longer and longer, proving that the moon is indeed spiraling away from the Earth, the barycenter of the Earth. So the moon, we have experimental evidence, is moving away. The measurements tell us that the moon is moving a substantial distance, 1.5 inches a year, which, you know, if you start thinking about it, for billions of years it's been moving away. It must have been much, much closer. Well, yeah, we'll get to that in a second. The energy that the tides pulling on the moon, the energy that the tides give the moon so that it spirals away, has to come from the Earth. You can't get something for nothing. So the Earth is losing energy, the energy it gives to the moon. And the way the Earth loses energy is it slows down. The reason it slows down is the high tide created, and I'm focusing on the one closer to the moon, but the same thing applies to the other one. The high tide that is closest to the moon tries to slide back under the moon because the moon's gravity is pulling that water. So the high tide is trying to get under the moon at the same time that the Earth is spinning away. And so the water in the high tide pushes clockwise, the Earth is spinning counterclockwise, and the high tide, when it encounters things like continents or islands and stuff, the water pushing on the continents slows the Earth down. So the friction between water and land is causing the Earth to slow down at about 2,000 2,000ths of a second per century. So does that mean that the Earth is spinning faster? Of course it does. And we'll talk about that too. So these are some of the major consequences of the interaction between the Earth and Moon. So that raises perhaps the question in your mind, does that mean that because the Moon is spiraling away, someday it's going to leave? And the answer is no. The Moon is not going to leave orbit. And the reason it isn't, I'll put up the words while I say it, the reason it is not going to leave orbit is because as the Moon spirals away, the orbit it has gets longer and longer. It takes more than a month in round numbers to orbit the Earth. The farther it gets away, the longer it takes. At the same time, the Earth is slowing down. So eventually, there's going to be a time when the Earth is spinning, rotating, at the same rate that the Moon is orbiting around the barycenter, orbiting with the Earth, if you'd like. And from then on, when the Moon is directly over one place of the Earth and stays there, there will be no more high tides pulling it forward because the high tide will be directly under it. So this situation called synchronous rotation. And from then on, the Earth-Moon system will be orbiting together and the Moon will not move away thereafter. Okay, so with that as background, let's take a look and see what the Moon has done for us. Okay. As I said, the Moon has been moving away. the best estimates, and again, this is definitely a work in progress, but in round numbers, the moon, when it first formed, was about 10 times closer than it is today. Having said that, it turns out that the tides are a direct, the height of the tides is directly related to how close the moon is. And in particular, when the moon was young, the tides from it, 10 times closer, were 1,000 times higher than they are today. Goes as the third power of the distance. And therefore, if Bar Harbor has tides of about 12 feet at its highest range from high to low, when the moon was closer, the tides in Bar Harbor, allowing that Bar Harbor existed, would have been 12,000 feet high, over 2 miles high, the tides. And at the same time, as I said, the Earth is slowing down. We think that the length of the day back then was about 8 hours long, not 24, 8 hours long. And there would have been, therefore, 2 high tides. There are 2 high tides every day. There would have been 2 high tides every 8 hours. But let's think about that for a second. These tides, I'll go to this picture and then come back. These tides roaring inland and then roaring back out, 2-mile high tides, would have scoured the surface of the young Earth tremendously and put a huge amount of the surface rock and other element substances into the oceans. And therefore, that rapid scouring of the surface, scraping of the surface, erosion of the surface would have created the primordial soup in which life formed. And therefore, life was able to start forming pretty quickly after the Earth-Moon system first formed and water developed on the Earth's surface. So that was a major contribution to the Earth from the moon. Okay, so what else? That impact that I showed you earlier on, remember the Earth, we think, was rotating around once every 8 hours, but the impact, we believe, caused that rotation axis, the north-south pole, to tilt about 23 degrees. And that tilt is what gives the Earth the seasons. So very, very briefly, here's on the top, the tilted Earth. The direction of the Earth's rotation axis stays the same throughout the year. Here's the Earth orbiting the sun. And and because of that, the sun is at different heights in our sky at different times of the year. During the winter, as we all know, the sun rises lowest in the east and if you will, the southeast. Its peak is lowest in the sky and it sets farthest south of west during our winter time. And therefore, the light, the energy from the sun is spread out compared to other times of the year when that same amount of energy is more concentrated and therefore provides more heat to the ground, giving us the different seasons. So that is something else that the moon's existence has given us, is the seasons. It turns out, and this is only very recently discovered, that the presence of the moon causes the tilt of the Earth's axis to stay about the same for billions of years. In other words, if the moon had never existed, the rotation axis of the Earth could change profoundly from straight up and down as it orbits around the sun, meaning no seasons, to a big tilt where the seasons would have been much, much more severe than they are now. So the moon has stabilized the axis of the Earth's rotation, as another thing that it did for us. The Earth has been slowing down, as I said, and therefore the day has gone from 8 hours to 24 hours, which of course is a good thing. Because think about it, suppose the Earth's day was 8 hours now, we wouldn't get done nearly as much in a day as we do in our 24-hour day. Furthermore, the changing rotation rate caused the weather to be considerably more moderate than it would have been if the Earth had been spinning faster. If it had been spinning faster, the winds would have been much stronger. There would have been many more storms compared to what we have today. And we have quite enough as it is. Another thing that the moon has done for us is having set the current time at about 24 hours and having kept it there for millions of years. It's slowing down slowly, remember. The 24-hour day has allowed the evolution of life with we have built-in clocks called biological clocks that are synchronized to the 24-hour day. So, for example, if we were to go to another world that had a 12-hour day, picking a number, an exoplanet somewhere that had a 12-hour day, our biological clocks would not allow us to function effectively there. We live in a world with a 24-hour cycle. Our bodies are designed for that. And going to Mars is okay because it's only a little bit slower than 24 hours. So if you want to visit Mars someday, that's not out of the question as far as your biological clock is concerned. But having said that, if the Earth had an 8-hour day, the biological clocks would have evolved very, very differently. And furthermore, the moon provides light at night. Different phases, of course, have different amounts of light. And animals use that light to navigate. So the evolution of animals would also have been different if there had been no moon. And perhaps the one of the other major things is we could go there. We could go there with when our technology was, relatively speaking, relatively primitive. If there had been no moon and the closest place to go was Mars, it would have been profoundly different for the technologies that would have been developed, because getting to Mars is even today hard, and getting back is virtually impossible. Perhaps the most important thing that the moon has ever done for us is romance. So it plays lots of roles. Finally, then, let's take a look at what the Earth would be like if the moon had never existed. Okay, number one, and hopefully from what I've said already, you now know most of the answers to this, or most of these punchlines. So let's take a look. The day would have been shorter. If assuming that the day was 8 hours long when it first formed, it turns out that today the sun creates about 1/3 of our tides. And therefore there would have been tides on that version of Earth without the moon due to the sun, but never 1,000 times higher than they are today. The highest the tides would be on a world without the moon would have been about 1/3 as high as they are today. And therefore, the flow of the water over the land to bring into the oceans the minerals necessary for life would have been much delayed, because the tides on that version of Earth would have been much, much less than they are today. the rapid rotation of the Earth would have, as I said earlier, created completely different weather patterns. Um, uh, I don't think anyone has actually run the simulations, but it would be very interesting to see what the Earth would be like weather-wise on that rapidly rotating world. Um, the seasons, the seasons. Remember, the seasons were created by the tilt of the Earth's axis. And as I said, without the moon, the tilt of the Earth's axis would have changed from straight up and down, meaning perpendicular to the path of the Earth around the sun. In that case, no seasons at all. The Earth would have randomly changed axes. And so sometimes there could have been times here in Maine where there would have been no daylight for months. And then other times of the year when the tilt of the Earth is very different than it is today. And there would have been other times when there would have been continuous daylight here in Maine. And that would have varied from every few thousand or 10,000 years. And therefore, life on Earth having to function with changing, profoundly changing seasons would have really been different than life on our Earth. As I mentioned earlier, the primordial soup would have been much delayed because the tides would have been much lower. And, oops, sorry about that. As a result of that, it would have taken much, much longer for life to form and evolve. I mean, it's entirely possible that life formed early at the bottoms of the oceans where there are lava flows coming out. But the problem is that without the super high tides that really occurred, the primordial soup would have been so thin that that life would have existed on the bottom of the oceans near the vents for millions of, perhaps billions of years before enough debris came into the oceans to allow life to come out and live on the land. And therefore, the life forms that would have existed on the Earth if the moon had never existed would have been profoundly different than it is today. And I think with that, I will stop, and I'll be more than happy to answer any questions that you have.
Oh, thank you so much. Fascinating. So many things to ask about. Terrific. The one thing, if you could clarify, when you were talking about the moon's impact on the Earth's axis, was it the impact of the I don't know what the term was that you used for it, but the impact that resulted in creating the debris field, the belt that eventually became the moon there, and that has that impact on the axis, and what role has the moon had on maintaining that tilt? Could you clarify that?
Yes, thank you for asking. Okay, so given the rotation axis of the Earth, let's say it was exactly perpendicular to the plane of its orbit around the sun when the Earth first formed before the moon was here, okay? Then there would have been no seasons because, I don't know if you can see this, but as the moon, as the Earth went around, the tilt, no seasons. The impact that I described was the thing that tilted the Earth over. And that created the seasons. In other words, if the impact that created the moon had occurred directly over the Earth's equator, had hit the Earth's equator, then it would not have tilted the Earth over. The impact of the Mars-sized body struck somewhere between the equator and the North Pole and knocked the Earth over as a result of that, that impact. Is that answering your question, John?
Yes. Yeah. Thank you. And so, if you to follow up on that, so the formation of the moon that resulted from that impact,
Yes.
what does that play any stabilizing role now or since its creation so that the tilt isn't going to change any further?
Absolutely. And the answer is yes. It turns out, and as I indicated, I think this is a relatively new result of the simulations that have been done. But it turns out that the spinning Earth is held at the present angle, about 23.5 degrees, because when it tries to change angle, the moon's gravity pulls it back and keeps it tilted at the same angle. So the answer is yes, the presence of the moon is keeping the Earth tilted where it is, rather than allowing it to wander all over and changing our seasons profoundly.
That's great. Another question, what happens when you were talking about eventually the moon and Earth are going to be in sync and we no longer have tidal changes, is that correct?
Yes.
So what about the sun's influence on its gravitational pull or other influence there? Will that, how much of an effect will that have on tides?
The short answer is none at all. I'll give you two versions. The real version is none at all, because by the time this event occurs, that the moon and Earth are in synchronous rotation, the sun will have blown up.
Okay.
So that, will ruin your whole day. And however, having said that, if the sun was still shining when this event occurred, then the Earth would be rotating very, very, very slowly compared to what it is today. And yes, as the Earth and moon orbit around the sun in sync, the sun would create tides on the Earth 1/3 as high as they are today, which would vary one cycle, high to low tide, every 6 months. Does that answer your question?
Yeah, no, that's interesting. Thanks.
All right, I sent you a question with the chat.
Oh, okay. Thank you. Let me get to that. Thank you. Question here, what size impact on the moon itself would be needed to cause change in the system that you've explained?
An interesting question. Assuming that we don't want to destroy the moon in the process, I would think that it's two things that go into answering that question. Number one, the mass of the impacting body, how much matter it has compared to the mass of the moon, say. And the second thing that's important to know is how fast the impacting body is going to strike the moon. It's those two things. You have to know both before you can get a definitive answer on what would happen if a smaller body struck the moon. If I was to give you numbers, assuming that the relative speed is the speed of the impact is relatively low, which it certainly could be, then I would guesstimate the impacting body would have to be at least 1/10 the mass of the moon or less.
Related to that, what if a new body of some sort entered into the gravitational pull of the Earth or the gravitational pull of the moon? How would that affect things?
Yeah, that's an interesting question too. For example, what if the Earth had two moons?
Yes, and you've written about that as well. So maybe could you elaborate on that?
Absolutely. It turns out that if the two orbiting bodies, our moon and the one that comes in and joins us, if they are orbiting at different distances from the Earth, and let us say for conversation's sake that the incoming body has the same mass as the moon, so we can talk about something concretely, then the moon that is closer of the two would create higher tides because it's closer, has same mass, but it's closer, has higher tides. And therefore, the new moon coming in, let's say at half the distance as our present moon, would create tides on Earth that are 8 times higher than the tides created today by our present moon. Half the distance, 8 times higher. As a result, the whole tide cycle on Earth would change, because the closer moon would be orbiting faster and would be creating higher tides. And the so what about that is, those higher tides pulling on the closer moon, remember the high tides are pulling our moon away today, well, the high tides created by the closer moon would pull the closer moon away faster than those same high tides would be pulling our present moon away. The bottom line is that over time, and it depends on the, all things considered, in time, the inner moon will spiral outward faster than our moon is spiraling out. And as a result, eventually, those two moons would collide and become one bigger moon. So the takeaway is that the incoming body going into orbit around the Earth, depending on its mass, et cetera, would eventually merge with our present moon.
Interesting. We have a question here, and that says, as I understand it now, the moon receives some energy from the Earth because of the tide water. I'm sorry, I'm having a little trouble reading this. It is pulled by the Earth rotation to to lead the direct gravitational direction. My question is that I would expect the energy of the tidal movement to be much greater under an 8-hour day than a 24-hour day, and therefore I would have guessed that the effect on the moon's direction would have been much greater than it is now, rather than the sort of linear relationship which I gathered from your talk. Can you explain which view is more accurate?
The answer is, when it was closer, it would have had much more effect. So if I said that the motion of the moon spiraling away from the Earth has been the same all the time, then I misspoke. When the Earth was closer and the tides it created on the Earth were higher, those higher tides would have pulled harder on the younger moon, causing it to have spiraled away back in those days faster than it is spiraling away today. So thank you for asking, and I hope that answers your question.
I have a question.
Whoops. Yeah, if you wouldn't mind posing your question through the chat feature at the bottom of your screen, that would be great. We appreciate that. I wanted to follow up on your point, Dr. Comins, when you were sorry, I lost my train there. Oh, the time. Can you give us a sense of how long ago all of this occurred and where changes took place historically?
How long ago the formation of the moon occurred?
Yes.
About 4.5 billion years ago. That number is being refined by studying the moon rocks to determine how old they are, how long ago the moon developed a solid surface. That'll give us an estimate as to when it formed. So it probably formed within a few 100,000 years, round numbers, of the formation of the Earth.
In your your reference to moon rocks makes me think about how the understanding of the moon and Earth's relationship has changed since we've been able to actually sample moon rocks, which we had to go get, but also there was debris on Earth that we were able to look at. Can you talk about what's happened in the last 50 years in our understanding?
Sure. Well, first of all, your point is very well taken, that there is moon debris on Earth. And where that comes from in large amounts is that the moon is being struck all the time by debris from space. That's what creates, for example, the craters on the moon. when debris slams into it. When debris slams into the moon, some of that debris is splashed off of the moon and away from the moon, analogous to what happened when the bigger body struck the Earth. And therefore, some of the debris that is splashed off the moon by impacts has fallen on the Earth. And those are the moon rocks that are found on the Earth that often found, for example, in deserts, because it's easy to identify, rocky debris there. So having said that, our knowledge of the evolution, not just the evolution, but the chemistry of the moon, the internal structure of the moon. Does it have a liquid core? Does it have a magnetic field? All of these kinds of things are continually being revised. For example, unlike the Earth, the moon does not have a global magnetic field. But we now know from being there that there are places on the moon where there is a local magnetic field. And we believe that that local magnetic field is created in different places around the moon by iron meteorites, iron debris that has struck the moon. And that iron debris is magnetized, just like a magnet on the Earth is, a piece of iron is a good magnet on the Earth. The local debris that we have discovered in different places on the moon with its magnetic fields creates magnetic fields sticking out of the moon, but not far out. And therefore, the moon does not have a global magnetic field, but it has a local one. This is something we found out in the last 50 years. Likewise, the chemistry of the rocks that are brought back and the moon rocks on Earth over the last 50 years have greatly refined our understanding of what it is composed of. And if you recall that there was a earthquake detecting device, seismic detector on the moon, and using that, we can use the impacts of debris today to determine what the inside structure of the moon looks like, because the shock waves that run through the moon are detected, and we can make images, computerized models of what the inside of the moon must be like for it to have the vibrations that we see on the surface. So those are some of the things that we've learned in the past half century.
Did we, before we went to the moon and brought back rocks, what was our understanding, or how did we know that the rocks that were the debris on Earth were actually from the moon if we didn't have the chemistry to at the time to understand the relationship between what's on Earth and what is on the moon?
That's an interesting question. To my understanding, we only were able to identify those that are moon rocks after we brought back samples.
Interesting. Here's an interesting question. The book Seven Eves envisions an event that caused the moon to break up into 4 or 5 pieces. What would be the effect if the moon broke apart this way?
Okay, if the moon broke apart, but did not break so hard that the pieces flew away from each other, okay? I mean, that if they flew away, then they would fly away. Some of them would strike the Earth, some of them would leave, some might stay in orbit, okay? So, I mean, that would be a major impact event. If it broke up into a few pieces and they were relatively locked in, still in orbit, okay? The bottom line is that they would either eventually come back together because of their mutual gravitational attraction, or it can happen that passing pieces of this debris going past each other, some of them could speed up and spiral away from the Earth, and at the same time, the others would lose energy and spiral down towards the Earth. So you could have conservation of energy is the bottom line. So you could have events where, some of that debris could come to Earth and obviously cause profound damage. It really depends on the relative speed of the pieces of debris.
We have a question. Did the oxygen stretched between Earth to the moon and back play a role in the combustion of causing life to form and terraforming Earth as we see it today?
Could you repeat that one more time, please?
Did oxygen stretched between the Earth to the moon and back play a role in the combustion of causing life to form and terraforming Earth as we see it today?
The short answer is no. And the reason is that when the moon formed, the Earth did not have oxygen in its atmosphere. The oxygen in our atmosphere came much later as a result of life. So it came billions of years after the Earth formed. The first atmosphere of the Earth was mostly carbon dioxide and nitrogen. And it is unlikely that that gas, well, it is possible, I suppose, that gas could have extended to the moon when the moon was young, 10 times closer. But by the time oxygen formed, the moon was so far away that the oxygen would not have extended to the moon and would not have affected, and that interaction would not have affected the evolution of life.
You mentioned the moon having moonquakes, and you also mentioned that we don't know what kind of, it doesn't have the same kind of
Interior.
Interior, excuse me, as the Earth. Can you explain how the moonquakes occur and what causes them?
Yes, absolutely. Most of the moonquakes are caused by the impact of debris striking the moon surface, which is all solid. And the impacting bodies coming in often have enough energy so that when they hit the moon, that impacting energy creates essentially a sound wave, shock wave, that travels into the moon through the other side and can bounce off the surface. And that's why geologists put onto the moon through the Apollo program a bunch of these seismic detectors, because if you have seismic detectors, a few of them, you can use the echoing bounces, the energy from the impacts to map the interior. Does that answer your question?
Yeah. Very good, thank you. If we, I mean, everything that has been put on there to measure activity or distance on the moon all occurred 40 to 50 years ago. What should, or what would scientists want to put up there now in order to, what would it be that they're looking for that they are not being able to gather with the technology that they've put up there now, with the instruments that are up there?
Well, that's a very interesting question. I mean, the good news is that most of the things that we want to know, we had equipment on the moon to detect. Now that we've been there and seen it, we will probably want to drill into the moon to get, hands-on debris, which can be analyzed there. It doesn't have to come back to Earth, so that we can get a deeper understanding of what's happening inside the moon. I think that is one of the key things that scientists are interested in. Likewise, by the way, on Mars, that kind of thing is underway to understand what's happening inside the world. So I would say that is the major, a major goal that we have for going back to the moon. I think that getting more of an understanding of the sizes of the impacting bodies that are hitting it. Those impacting bodies are coming in so fast that completely pulverized, most of them. And that's why the moon has a smooth surface, a regolith, rather than it's all rocky. But understanding how much of different sized particles are striking the moon will then enable us to better plan for the habitats that we will eventually be building there, so that they will be structurally safe for people to live in. So those are things.
That's great. You mentioned Mars. What would be the impact, if any, of life on Earth or Earth itself if we didn't have Mars or if we didn't have Venus?
The short answer is not much. It is possible that their formation at about the same time as the formation of the Earth, their formation may have had some effect. But to the best of my knowledge, computer simulations have not shown definitively that either of those bodies is necessary for us to have life as we know it. Although, having said that, it is likely that because we have what is out there, the body that struck the Earth, the Mars-sized body, if Venus and Mars had not been there, the path of that body may have been very different. It may have never come here in the first place. So just a sort of a second-hand effect, which had a profound effect on life, but otherwise, I would say that they are not essential.
Oh, that's great. Before we go, I need to ask you about the emoji or the figure in Japan that is of you. Could you tell folks what that story is about and how that came to be? Because you are a character figure in Japan.
Yes, for those of you who ever went to a World's Fair or World Expo, each country and company at one of these events has their own pavilion, and each pavilion has a theme. And in 2005, there was a World Expo in Nagoya, Japan, and Mitsubishi, small company, you may have heard of it, its pavilion at the World Expo 2005 was entitled "What If the Moon Didn't Exist" by Neil F. Comins. And for that expo, I created or helped to create a 3D cartoon environment where people could sit in and watch a lot of what we were talking about. What if the moon didn't exist? And I was the cartoon character that described what was going on. After the expo closed, then for the next 18 years, that show was moved to a resort in southern Japan, House Tembosh. And for the last 18 years, then I've been that cartoon character in Japan.
Very good. I assume you're not recognized on the streets based on your cartoon character, but maybe.
I think it's called an NFT now.
Okay. Oh, there. All right. That's great. Well, with 1 minute left, we had a question in that I think everybody would be interested in. It says that with the current search for life on planets orbiting other stars, it sounds that like the existence of a moon may be essential for those planets to have life. Is that a true statement?
I would say that the presence of a moon would expedite life, would cause it to occur much, much more rapidly than without a moon. But it is entirely possible that other dynamics impacting bodies, for example, causing moon quakes on that other world that would put debris into the oceans, could also allow life to form. So I would say the moon would not be necessary, but it would definitely help in the process of forming life.
Well, Dr. Neil Comins, thank you so much for this fascinating presentation and for all the work you do for the university as a teacher, researcher, and public servant. As I mentioned, this recording of Dr. Comins' presentation will be put on the university's on the University of Maine Alumni Association's YouTube channel, and it will be there. And we'll send out that link to everybody so you can share it with others as well. But on behalf of the Alumni Association, thank you so much. It was fascinating. And also thanks to Aisha Veer, who was our person who handled the organization of this webinar and the technology that we use today. And also thanks to all of you for your participation. Our next planned webinar for the Alumni Association is on April 14th, and it's going to feature 3 prominent UMaine alumni who have been involved in diplomacy over the course of their careers. 2 of them are former US ambassadors, Ambassador Pamela White and Ambassador Ann Hall. And the other person is retired 4-star Admiral Gregory Johnson, who was a leading figure in Europe as the head of the US forces, naval forces in Southern Europe. So that will be on April 14th, and we'll send everybody who registered for this event an invitation to that as well. So on behalf of the Alumni Association, thank you all so much for participating and wish you the best. Take care now.